This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
People who listen. Was the recording okay for Wednesday? Did anyone check in the beginning? The beginning wasn't there, right? Nobody checked it? Well, you're here, that's, All right, very good. So let's start. I was talking about the mid-semester test. I have sent an announcement and put a lot of detailed information to LMS under feedback and assessment, appropriately, I hope, classified there. And, have a look. I will have an extra consultation hour next week, Wednesday afternoon, in addition to the Tuesday afternoon, 5 o'clock. To answer your questions. So I don't do email. I've been answering questions over email because only few people asked me, but if 30 people ask me questions over email, it's impossible for me to answer them. So then I will have to stop everything I do and answer questions over email. Therefore, please prepare your questions, come to the consultation hours. We do, face-to-face discussion, which is much more productive and meaningful. And also, there are no workshops next week, right? So gives you time. Also, Wednesday, Tuesday sessions. You can use that to prepare for the mid-semester test. And any other questions regarding the mid-semester test? Yeah, let me know. But I think it's quite clear. You can bring one sheet of paper, A4, both sides, handwritten. Don't photocopy everything into one sheet. I will take it away. So it has to be handwritten, and then you don't have to memorize much then, right? So, and you're also responsible to some extent from the, this is important, yeah, to some extent from the workshops, in the sense that what you have done in the workshop, I may kind of embed that to the question in a sense, like your understanding experience. I want this subject to be very integrated with the practical side. I will not ask you to write Python code, but I may ask you to write pseudocode. And I've put a link to what the pseudocode means also into the LMS, right? So pseudocode means just you don't have to remember how Python syntax is. You just write it like regular language. And everything is almost acceptable as pseudocode. So that's more convenient. I know some subjects ask you to write MATLAB scripts or something that I find it extremely meaningless. Who cares how the syntax is? So you do that already in the workshop, and there's a workshop manual. Any other questions? I think I've explained things. There is no precedent. I will ask very basic questions. Focus on the basics, the fundamentals, what's in the slides, and you can't go wrong with that, I think. All right? And it's just 10%. It's just a warm-up to the final. Okay, so maybe we'll discuss more during the consultations next week. So let's finally start with the machine learning. And I was making bad jokes. We left it there about data. And I also said deeply philosophical things. So let's get to the machinery of more down-to-earth stuff. So it's a set of data points, right? So we have a set of data points, X, and they are usually unordered. And if they are ordered, then it's a sequential chronological data, right? Then it would be then it will be a time series. I will discuss that quite later. For now, it's just a set, right? Unordered set. And then these are, for now, I'm kind of looking at R to the N. So these are vectors. And as you know, we live in a digital world. That means every data point can be anything. It can be an image. It can be a song. It can be any secondary characteristic of something. So these are the data points. And then, when available, we have a set of corresponding values or labels associated with each data point. So x1 may be associated with a y1. Maybe there is a function, multivariate function that f of x1 is y1 and f of x2 is y2. Right? This would be this case. And that's what's used in regression function as estimation. Or it could be categorization. So y might be just 1 or 2. Then x's, so for example, x's could be the pictures of dogs and cats. And then 1 is the dogs and 2 is the cats that then you will have labeled pictures, right? Or the songs that you like and dislike. Or it could be multi-category classification problem. Then you have labels that are, belonging to a finite set. So, handwritten data set, which then you have 10 digits, and then handwritten digits data set, very famous MNIST data set that you see. Then each X1 will be then picture, and then Y1 is one of the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So out of the 10 options. Good. So I have also put this slide about representing data, and just to show you that you can actually convert everything back to real numbers if you are in a pinch. If data, for example, belongs to one of the classes, X belongs to one of the classes, then if there are, for example, 4 kinds of jobs, there's a movie called like this too, and then you can map each of them to some vector, basis function, vector, and then represent them with the vectors. Or it could be ordinal, ordered data, it could be the grades, and then you map them to 0, 1, 2, 3, 4, 5. Or it's numerical, which is the regular case that I already mentioned. So you can actually convert almost everything back to numerical in most of the cases. I'm sure there are edge cases that I cannot think of right now, but most of the time you can convert the things that are not number-like looking and map them to numbers and deal with them through the usual libraries and methodologies. Things are quite interesting when you kind of access the DNA sequences and so on. Biology people play with that. That is really interesting characteristic. You have a very long vector of 0, 1s, and then you may want to do something about it, and then transform it maybe to make it easier to deal with. But that's a specific case. All right, is this much clear? Yep. So what are the learning tasks? So, okay, we have data, right? Now we want to learn something, whatever that means. It's a bit actually quite vague, whatever that means. Therefore, it's better to talk about learning tasks, which is a bit more defined. There are 2 big categories, supervised learning and unsupervised learning. In supervised learning, you have these not only X's, but you have also the Y's, regardless of what Y is, right? So it could be a real number, then you are trying to learn a function, or it could be, 2 categories, then it's binary classification, whether X belongs to Y equals 1 or X equals to Y over Y equals 2. So that would be a binary classification, binary because it's only 2. It could be multi-class category classification as well. Regression is I'm trying to learn a function, but I have this set of X and Y's as a given to me. So I have already some previous knowledge. Somebody labeled these things for me. I have examples in front of me. So then what I do is usually I take that set and divide it into training set and test set. I will come to this. And then run my training algorithm on the training set and test it on the test set. Right? So supervised learning is that in a kind of a high-level presentation. Unsupervised learning, you only have the X's. There are no labels. You have only the data, and then you want to say something about the data. Maybe it's a very interesting data set. So that is actually very closely related to data mining and so on as well, the hot topic. So you can do the basic thing that everybody comes to mind first is clustering. I can take the data and then divide it into pieces, clusters, categorize them, categorize the data set into pieces. And then the pieces are more similar to each other than the other pieces. And I will come to what I mean by that. Or you can do anomaly detection. You can take the data and then see what is the normal data, and then are there edge cases? The edge cases tell you these are anomalies. Maybe you need to do something about the anomalies. They might be indicator of the machine not going to work, or it could be a security issue. A lot of the normal things are the normal behavior of your users. The edge cases may be indicative of someone attacking your network system. That's another important learning task people have been dealing with. Then another task is online or sequential learning. As I said, I'll come to this. You have a time series data. how a system evolves, for example, maybe a process, control system maybe, or it could be an economic system, economic data, or it could be, just this morning I was preparing the slides for sequential, so it's very fresh on my mind. And then it could be medical, or it could be anything, right? So, but the key point is sequential, and then if the new data comes, you want to update your learner and do something with it, maybe do classification or anomaly or anything else. And the last one we will also touch towards the end of the lecture is reinforcement learning. That is interacting with the environment. Actually, I will do sequential learning later as well, so I should update this slide. Reinforcement learning is you interact with the environment, so you don't have a ready data set, but you have an environment that gives you data as you take actions, and you have a presence in that environment, and then you try to achieve a goal, right? So that's a bit different from the regular static learning tasks. Even it's different from the online learning. So there are a lot of different concepts here that I will come to. So let's start with the supervised learning. So I have said many things, so let's make them a bit more tighter and more precise. Supervised learning, the focus is on accurate prediction, right? Either I'm predicting the value of the function or the class of the x point, right? So that is the focus. In unsupervised learning, the aim is to find compact descriptions of the data. Data doesn't have any associated values or labels with it in the unsupervised learning. Therefore, all I can do is I'm trying to describe the data, you know, as I was saying, categorize it, maybe cluster it, and get its characteristics, maybe find its distribution, right? Probability distribution, adopting a probability point of view. So again, adopting a probabilistic point of view, which is often done in machine learning, and actually there is a whole class of people for whom machine learning is just statistical learning. These are more statistical oriented people. So for them, the whole machine learning is all about probabilities, and they love their probability models. I should warn you, that's not the whole picture, you know, because there are also parts of machine learning that don't necessarily need to be seen from a probabilistic point of view. You can actually happily do that too. We will come to that. One good example is support vector machines. You don't have to put a probabilistic view on support vector machines. You can, but you don't have to. So in supervised learning, our interest is describing why conditioned on knowing x. You know, what is the y coming from x? Of course, we want to create we want to learn a model. I guess this is very implicit. I should say it more explicitly for the newcomers. So once you have a set and you learn something out of it, x-y relationship, the whole goal is if a new x comes, I want to be accurately find the right y, right? So this is the whole idea. So it's not about what you have in hand, but if in the future similar data comes your way, once you have learned it, hopefully you will perform very well with the new data too. So that's the whole that's a very underlying concept. So from a probabilistic point of view, the probability of y given x, I also added this here, d. It is also implicit. What is the probability of y given x and the data I have? And the model, actually. I can even put a command, put an m there too. Because I am learning within a model. I make a selection of the model. I have my data set. Given my data set and model, what is the probability that having a y given the specific new x? So there is a long definition here which summarizes what I've been talking about in a more precise term. But notice that the whole idea is after you learn, when given a novel input x star, the predicted output y star, we want it to be accurate. So the pair x star y star is not in the original data that you have used to train your model, learning model, but assumed to be generated by the same unknown process, right? And then we want to make sure that our y star is really the correct one when the new one comes. Of course, you need to have an oracle to tell you whether it's correct or not. You need to double check it. How do we do that is in the next slide. So another, we can actually look at it from also an optimization point of view, right? We want to minimize the error, and I can describe the error as an objective function, right? And then that would be a loss function. So loss function of L, y predicted and y true, right? How much my predicted one deviates from the true one, assuming you know the true one. I'll come to that. Or conversely, you can actually make it an U equals minus L utility function. Minimizing loss is maximizing utility, as you know. That's the same thing. You know, some books talk about maximizing utility or minimizing the loss, and loss function could be the error function, one-to-one mapping there. But you know now probability, so that's good. We know we don't get confused by that. Now I mentioned this whole true y and the predicted y business. How do I do that? Like who tells me the true one and so on? So this is how you do it in supervised learning. Right? We are talking about supervised learning here. There's a y and there's an x as well. The underlying assumption here is the novel data that will come my way has to have the same characteristics. For example, from probabilistic point of view, distribution as the current data that I already have. Otherwise, you will need magic. Right? So don't expect magic from machine learning. So your new data is drastically different from your training data, you will fail. Well, why should you succeed, right? There is no magic bullet here. So all you do is from the training data, you learn something, you learn a model, and then of course the new data looks like the training data, then you're in good shape. It will perform well. If it's drastically different, yeah, you're lost. Make sense? Yep. So given the current data set, what I do then is how am I going to know this loss function though? There is this issue that, you know, loss function says I predict something and the true one and I need to find the difference. But what is that? Who tells me that true one? The issue is I have only the given data set. The future data hasn't arrived yet, for example. So what I do is very simple. I divide my data into pieces, training data and test data. So what I do is I train my model using the subset of my available data, which is the training set. And then what can I do? Because I have divided in a random way usually, I subsample the test set out of the training set, divide it by 25% to 75%, let's say. That 25% belongs to the same data set. I know it is characteristically very similar to my training data. They come from the same data set. Therefore, it's a fair game in the sense that assumption is satisfied. And then actually, I train on the training data and test on the test set, as the names indicate. Then that will give me some error, because the test set is not the same as the training set. And it will be cheating if you test on the training set. Obviously, right? But it's a very fundamental mistake people make, right? I mean, I have, over the years, students who don't know much machine learning, they say, I told them, oh, watch that MOOC and learn a bit machine learning. They said, oh, I learned it, came back, and then they trained the model on the data set, and I said, okay, did you test it? They said, yes. Did you test on what? Then they said, on the same set. That doesn't make sense. Of course, it will perform very well. You need to test on the test set. And then, as I say, future data hopefully matches this. There is a more sophisticated way of doing it if you have the computational power and time. And that's the cross-validation, k-fold cross-validation. There the idea is nice and quite logical and simple. So let's say I'm, again, doing this one quarter to 3/4 separation. Usually 3/4 is the training and 1/4 is the test. K-fold, here this is 4-fold cross-validation. That means I take the white ones as the training set, then test on the red one. Then this is one model that I train. Then I leave that aside. I retrain the model from scratch, from x0, and take these 3 as the training set and this one as the test set, right? The red one. And then I leave it aside. On the third one, I take the other one, and this is the test set. And the fourth one, the other quarter, is the test set. Then I look at my performance for each case, and I report the average performance. That is actually a nicer way of, validating, cross-validating your model. And this is probably the best you can do, because you have only a finite data set. Right? Given the finite data set, you divide it in different ways. Makes sense, right? Maybe? No? sklearn has standard functions for this cross-validation. There's a just single command, and it's also the training dataset division. There's a single command that does it automatically for you. You know, if you are clever and lazy, just use the library, and then it gives you the result. All right, this is really important, so everybody should perfectly understand this. Maybe you already knew this? No? Okay, it's new. Some people say it's new. That's good, because it's a new subject. That's why I'm offering this. All right, so let's look at this, you know, classification versus regression business, right? So let's look at it a bit more closely. Classifications assign each input vector, x, to one of the finite number of discrete categories, right? So I have the vectors x's. As I said, they could be anything, picture, you know, process properties, audio, you name it. And then you map it to one of the categories, as I said, n categories. Binary classification is there are only two categories. So you take x and then x belongs to one category or the other category, right? This whole classification categorization thing is very old, right? It goes back to Aristotle. The ancient Greeks, they were categorizing things and classifying things. So this is a binary. The output, you give an input to x, and then your learner should tell you a kind of a discrete output and a binary output. Regression is the output. If the output is continuous, then it's a regression problem and learning a function. So you learn a function there. So the pictures are not bad. So binary classification, you have data points, then you just, here they are nicely, you know, it's easy to discriminate them, right? I will draw a line, anything this side of the line will belong to this circles, and then anything on the right-hand side will be crosses. Multi-class classification, you see there are three classes. You know, I have the rectangle, you know, squares and triangles and x's, right? And then this is a way of doing linear regression, right? I mean, I have a data cloud. Most of the time, real-life data is messy and noisy. So you say, okay, I'm going to fit a linear, affine function. It's not a linear function, it's an affine function. Y equals ax plus b, right? For some ab. And then you can fit a nice function here. So you are learning the function from x to y. Huh? Make sense? So, for example, also I did a box here. Let's see. So the tomorrow's stock price based on the past observation, right? And this is a form of supervised learning. This is a sequential version. This data doesn't have to be sequential, but it can be sequential as well. And we can actually look at the times and the prices, and then we can do the prediction. And that would be, you can actually approach it as a regression problem as well, looking at the last 100 prices and map them to the next price. That would be a function learning. You can see it as a function learning as well. But if you do that, even if you use the most sophisticated thing, it will not make you rich in real life. Can you imagine why? It goes back to this underlying assumption, right? So what happens in the world is the world is not a stationary place. It keeps changing. The factors change, you know, in a very unpredictable way. So underlying properties of the stock market and behaviors change. Everything changes. So yeah, it's very hard to make a long-term prediction of where the stocks will going to go. Otherwise, you will be all rich here. Or I will be rich here. I wouldn't be here teaching you. So, or maybe I will teach just for the fun of it. I will be still here. So it's not stationary. I will come to that. But yeah, the whole underlying assumption, don't underestimate it. I met actually a professor, and I was telling him this. He didn't understand. He said, why can't I not predict? I said, mate, it is non-stationary. The world changes. You know, something happens in some country, it affects the whole stock market. How can you predict that? There is no stationary distribution that, you know, underlies that data in a constant way. But yeah, I couldn't convince the guy. So, really, I'm not joking. I was a bit, I mean, maybe he was joking with me, but he seemed quite serious. So To this day, I'm still scratching my head. How did he think that using signal processing or machine learning or whatever, he can predict something that is not stationary? Like, it's like magic. Okay, so now you know, right? You will not say nonsensical stuff like that, or if someone tells you nonsensical stuff, politely smile and say, yes, yes, you will be rich. Yeah. Only way this works is high-frequency trading. When they trade under a second, you can actually make assumption that the next window of 1 second is stationary. Nothing changes that much in 1 second. Then, yeah, you can actually, that's what high-frequency traders do. Within 1 second, the world doesn't change that much, right, compared to the next day or hours. So actually, they actually make this very fast trades during that interval, and then these algorithms would work indeed, and they are working. But it's a bit cheating. Actually, they are cheating the stock market. That's a different discussion. Okay, so now we come to this unsupervised learning business. Yeah, as I said in the very beginning, remember introduction week, the subject is not about data mining, not because data mining is not interesting, but I don't have the time, and I wanted to make it a bit more engineering. Data mining is kind of slightly beyond engineering in certain senses, but it can be applied to engineering as well. So we will do some unsupervised learning, but we will not become an expert on data mining out of the subject, unfortunately. Or data science is a different story. I should design a whole new subject for that. There is one, I think, somewhere. In supervised learning, given a set of data, the aim is to, okay, this is very interesting, right? The aim is to find a plausible, compact description of the data. This is as vague as it gets. You know, this sentence doesn't mean much. Then an objective is used to quantify the accuracy of the descriptions. But yeah, so from a probabilistic perspective, we are interested in modeling the distribution P of x, the generative, maybe that's a generative model. What's the probability distribution of the x? If x is a vector, if I treat x1, x2, xn as the random variables, then you have a joint probability distribution, right? I assume also you know probability to some extent. I hope so. You can brush up your skills from Margaret's subject or wherever you learned the probability. The likelihood of the model to generate the data is the popular measure of accuracy of the description. So then given the probability, probability distribution, how likely will I see this training data that I'm seeing now? And then I will discuss this a bit more in detail, this maximum likelihood idea. I already mentioned it in a problem, but we will go a bit deeper into it because it's central to many of the things that's been done in machine learning, including neural networks. Clustering. So one way to find a plausible compact description of the data is grouping the set of objects in such a way, clustered objects, as the collegial name indicates, right? So this is again a bit vague, right? Grouping a set of objects in such a way that objects in the same group, called a cluster, so the objects in the cluster should be more similar in some sense to each other than those in the other cluster. So that's the whole idea of clustering. The problem is how many groups there should be, and what do you mean by similar, and what do you mean by dissimilar? So these are all need to be defined, and we will define them. But still, a lot of vagueness, a lot of freedom of choice here that makes this problem problematic. Actually, it is well known that clustering is a fundamentally ill-defined problem. You don't get a clean solution. Because of this vagueness, even in objectives, and how you measure the objectives, you get multiple solutions. Because it depends on how you answer these important questions. What is the plausible compact description? Which object represents the accuracy, objective represents the accuracy of the description? What is the similarity measure you use? You use one similarity measure, you will end up with one clustering scheme. You use another similarity measure, you end up with another clustering scheme. Which one is the right one? How many clusters am I going to get? These are almost impossible to answer, or you have many answers. So there are metrics, but they don't provide the magic criterion to apply to all cases. So the metrics are also not terribly useful. So therefore, what you do is actually you use human expertise, or you use an outer loop to evaluate the clusters. Either humans look at it and say, this is a good cluster. So you are subjectively deciding, because as I was saying, there is no objective answer to these questions, or there are multi-answer questions. Or what can you do? You can actually, if you're doing clustering for a purpose that you use afterwards, you can use the afterwards purpose to see if that clustering works for me or not, right? You don't have to always have human in the loop. Maybe you're doing clustering for some engineering task, and then you can use different metrics to get different clusters and then give them to your next stage, and next stage, you see how the next stage performs, and you can dictate then back which clustering worked for me for that specific task. You see, that's also one way of getting a kind of a concrete answer. Does that make sense a little bit? Yep. So you see here, how many clusters are there? I mean, this data is a synthetic data that's also in the 2Moon data. You need a nice complicated boundary to separate them if you do classification. I kind of labeled them. You see, this is labeled red and blue, but in reality, you may have just the unlabeled two moons and noisy. And how many clusters are there? Subjectively, I would say 2, but this very human, you know, if you ask me, how do you know that? Why not 4? Why not 6? Same with here, or same with here. Why do I not put these 2 separate clusters? Why don't I do any cluster out of these 3 points? You can, then nobody will say wrong. It will be just another way of doing it. Like then, if I have 3 clusters, looks okay. But why don't I do 1, 2, 3, maybe this one's 4, 5 clusters, all equivalently valid. So yeah, clustering is ill-defined. So there are a lot of local minima, even if you choose an objective function. And then you decide how many clusters you want and so on. All right, so that's, yeah, data is real life, and real life is messy, right? You don't get exam answers type of situation here. Any questions on this? This should be also quite clear, hopefully, to you. What are the gotchas and so on? Any questions, comments? Nope. All right. So we go to anomaly detection and online learning. So this is, I'm kind of mentioning these briefly and then pass them. They are kind of, once you know the basics of supervised and unsupervised, these are almost special cases, but they are big enough to deserve mention as a learning task. Anomaly detection is about identification of anomalous or rare data points, which differ significantly from the majority of the data. And then also known as novelty detection. It's a good name. So that is the common thing happening here, and what is novel, new things. So you see here, this is a good example. You have an engine, aircraft engine, and you look at the 2 features of it, heat and vibration, and the X's show normal operation. But if you see some high heat and low vibration or some combination of it, maybe the engine is not performing as it should. So this anomaly detection, detecting those points, might help you a lot in the engineering setting, right? So, or security, as I was saying. So this is the normal behavior of your users. Suddenly you see strange traffic on your network. Maybe X1 and X2 are the traffic from locations to destinations. Then you get suspicious. Am I being hacked or something? You know. So that anomaly detection is important. And you see, it can be seen as a clustering task, and it can be seen as a classification task. So you can use both methods for handling this. You can cluster the normal points, then anything that is not clustered in the normal will be the anomaly. So you can use clustering, or you can use straight classification. You draw a boundary, and then anything beyond that boundary is anomalous. Hard to do, though. This is 2-dimensional. If you have an 100-dimensional data, what does it even mean? It's an intricate question and difficult question. And online learning, I think I mentioned this a little bit for the stock market. Or you can try to predict the weather, which is also very important, right? So how am I going to predict the weather? This is a really nice graph, by the way. If you find the time, have a look at it closely. This is from ocean currents and sea surface temperature anomalies for the, I think, Pacific Ocean, which affects the Australian climate quite a bit. And then the anomaly, they try to predict the anomaly because if the anomaly goes to the red region or the blue region, it has a lot of implications regarding drought or rain in Australia. So So it affects the livelihood of people. So you want to try to get this right. But you do it in an online fashion, right? You need to do it as the data comes. You update your predictions. And you see all these curves. They are the family of predictions they have done. Then they take the mean of it. So these are all possible. Each method gave them a different prediction. Or maybe the parameters they changed. So online learning can be supervised or unsupervised. So that's in general. You can also do it that way. Okay, so that's the two other tasks. So, but we will focus on the supervised, unsupervised, mostly on classification and regression and clustering as the main things, fundamental things to learn. Again, any questions or comments? This looks like a lot of verbal stuff, but these are really at the heart of the matter, the basics, as I call. So now I will switch to model selection and overfitting in linear regression. I will start with linear regression because it's very, very, fundamental 101 machine learning task that everybody knows and talks about. And then I'm going to use that to talk about the important concept of overfitting and model selection. Right? I'm going to use that as an example, and building on the example, I will talk about more general things like overfitting and model selection. The issue of overfitting, underfitting, and model selection is applicable to more than linear regression. It's applicable to almost all machine learning tasks. So just to make it clear, right? Well, linear regression becomes my motivating example because it's easy and simple and easy to understand. So I'm giving a data. I have a data set, X and T's, not Y, because different books use different ways, labels T's. Okay, that's fine. And I want to find a model, function, a curve, right? In this case, the model is a function, and the function is a curve, to represent the data to estimate T star for new X star, not in D, right? This is a very concrete example of what I've been talking about. And the data is really nice. There is this sinusoidal curve, and then I added some noise to the curve and created these blue data points. There are n equals 10 data points. Of course, you don't know the green function. So you only have the blue data points. Right? In real life, nobody gives you a function or probability distribution. They give you the data. So that's where mathematicians and engineers and non-mathematicians differ. Mathematicians live in the world that there's a probability distribution. Right? That world doesn't exist. There's only real data. The probability distribution is just a model of the data. So you have only the blue points. Maybe they were generated by this. In this case, you have generated the blue points. Of course, you have the ground truth. You're the oracle. You know the basic. You have generated it. Therefore, of course, these points come from the sinusoid. In real life, though, someone just gives you a data set. Then anything else you talk about, it is an explanatory model, right? So this is important to also understand. One approach is to use a polynomial function. Okay, so you say, oh, these blue points, they look like a polynomial to me. Obviously, the linear model, maybe it won't work that well, right? So, and then also you don't know it's sinusoidal, so you see maybe it's a polynomial. So let's use that one approach, use a polynomial of degree m, and we parameterize the polynomial model. So then the function model that I'm imposing is just this, right? So this is an mth degree polynomial. Yeah? And I don't know w's, omegas and w's. So that's the task. M is a hyperparameter. I will say it again. So I made a pre-choice, right? So with M. If I made the bad choice on M, then I'm in trouble, as you will see. I may choose it too little, too high. Okay, then, all right, I have the problem. I have the approach. Very nice. What is my goal? I want to minimize the error between my estimates and the data, right? So what I do, of course, with respect to the test data. So I need to take these 10 points and use maybe 7 of them to train my thing and test it on the other 3. Because this is so simple, I can do cross-validation. In reality, of course, you won't have 10 points. You will have like a lot of points. So that won't be an issue. The error criterion, how about mean square error or just error, sum of squares error? Does it matter if I put a 1 over n in front of this? from optimization point of view? If I minimize f of x or 1 over n times f of x, where n is a constant, does it matter? It's the same thing, right? So mean square error or sum of square errors, in this case, it doesn't matter at all. Yeah. So, all right. So now I have, let's write the model in a bit more general way. This was the example with the polynomial, but it doesn't have to be polynomial. It can be any function of x, phi of x with the basis functions. Like here, if I write the phi of x, you see I can write it a degree 3 polynomial. Then the phi of x would be 1 to x squared x cubed, 1x x squared x cubed. Then y of x would be then w transpose times phi of x. It would be this. Right? Just focus on the example here. And this phi of x doesn't have to be 1x x squared x cubed either. It can be any sequence of basis functions of x. But if I write this way, then I can take the data and write the square error. And here the notation is n is for data point. So I need to do the error over all data points in my test set, in my training set, because I'm training now. I'm not testing yet. So this is all about the training set. Right? This data is the training set data. That's kind of implicit also. You need to kind of see. And then because this is square, I can write it this way. And you see this is a square function of error in terms of w's. It turns out this is a nice convex optimization problem. That's not even constrained. W's are not constrained unless I constrain them. And then because it's perfectly convex, I can take the first order necessary condition, which becomes also the sufficient condition. I take the derivative and equate to 0. And I have tried this at home. You can also try at home. When you take this and take the derivative and equate to 0, remember these are vectors for each n data point. So this is not to the n. It's a bit bad notation as I footnoted here, because I took it from another book. Then you just play with it, and you get the derivative equals 0, rewrite the terms, you get a w in terms of inverting this matrix and multiplying with this, or you just write the equation and solve through this set of equations, right? So there are different ways of solving equations. You can use Gaussian elimination, you can use matrix inversion, you can give it to the computer and let it solve it. There are linear equation solvers that are quite efficient, right? Numerically, you can solve it. So that's what you do. So essentially, what I'm talking about here is this is called a linear model because the parameters that I'm learning are linear in the basis functions, which are predefined. And you see the parameters and the basis functions, the basis functions are linearly combined. Omega 1, phi 1, plus omega 2, phi 2, omega 3, phi 3. That's a linear combination of the basis functions, function of x. And because I know all the x's in my data set, so that's a linear model. And then I can use basic optimization and find the best w's that will minimize the mean square error. All right? Right? So yeah, I will not, because this is just taking derivative of a vector and so on, I will not really spend time on this. But as I say, you can take the time and have a look at it and then verify it for yourself. I will do an example. Do we have? Yeah, we have time. Maybe if 5 more minutes, maybe we can do this question. So there is this hyperbolic tangent function, and then the logistic sigmoid function. These functions appear a lot in machine learning in different places. So and this question is just playing with them. So we show that they are related by this. So you can write one in terms of the other. A is the input, x here. And then once we know this, we can show that the linear combination of logistic sigmoid functions of the form. So you see this is a model. Instead of phi, you have sigmas. Logistic functions are the basis functions. And then they have additional parameters like mu and s, so in addition to w. And then maybe these are predetermined. So I choose some basis functions with their mu's and s's. And then x, they are functions of x. And I make a linear combination of them with, again, weighted. And then there is another bias term, omega 0. And then one can show that this is equivalent to a linear combination of tangent hyperbolic functions when you make a small change. And then, of course, your omegas will not be omegas anymore. You need new parameters u's. But then it will be the same story. So this shows you that sometimes you may use a different model and you will get different parameters out of that model. But that model may be closely, equivalent to another model as well. So this is possible. It doesn't have to be always, but in this case, there is a close relationship between two seemingly different functions, sigmoid and the tan hyperbolic. So let's do this, as I was saying, and then it also gives us a chance to play with linear models. Yes, so sigmoid is. So let's get a. What is this? Yep. So sigmoid is actually, in terms of a, that is 1 over 1 plus e to the minus a. If you write it, in terms of a and sigmoid, so at 0, a equals 0, you get 1 over 2. So that would be 1 over 2. And then a goes to minus infinity, the denominator goes to infinity, you go to 0. So you asymptotically go to 0, come to 1 over 2, and a goes to infinity, e to the minus infinity is going to 0, so you go to 1, right? So you go to 1. So this is how sigmoid looks like. Asymptotically goes to this, and it squishes things. Like it takes a and squishes to between 0 and 1. Yeah? So it serves that nice function of squishing the input to a finite range. So if I write this tangent as the 2 sigma 2 plus, so let's write this 2 sigma 2a minus 1. So that would be then 2 over 1 plus a to the 2a and minus 1. If I subtract it, then minus, make the denominator and numerator the same as this one. So we get then 2 minus 1 and minus. So you get 1 minus e to the minus 2a divided by 1 plus e to the minus 2a. Yep, and then you multiply maybe with e to the a, numerator and denominator. So we get then e to the a minus e to the minus a, and then e to the a minus e to the minus a. And that's actually the definition of this plus of tangent hyperbolic a. So that's the definition of it. So the first part is easy. There is nothing here, some basic algebra. But we get exposed to these functions. At some point in neural networks, these two functions were the very popular functions. Sigmoid is still widely used at the output layer. I'll come to these when I discuss the neural networks. So we will see these guys later. Actually, this is even more important, so I should make it red. Okay, so that was the part A, so to say. And then part B, if we take, so we want to show, we want to start with this 101 equation, and then we want to end up with this other equation. So this is also easy to do. Actually, you see this tells us a little bit how to do it. If I write A as Aj as x minus mu j divided by 2s, 2 is a bit like magic, but bear with me, because I want to bring it to sigma 2a. That's why I put the 2 in the denominator. So then what I have here, then from here, I get y of x is omega 0 plus sum over j, 1 to m, omega j, and then that would be then sigma 2aj, right? Because of this, you say let this be defined as this, then I can write it in terms of sigma. Very good. And I can also do this, right? I can also subtract minus 1 and add plus 1. That will not change anything, right? I can do that too. But then I have the expression that the question is shouting at me, that is giving me the tangent part, right? So this will be then the tan h part from the first part of the question. But then there's a +1 that's sticking still. So I need to kind of deal with that. So y of x omega, or v, or w. Then I have what? Like I have this one, plus if I do the one that is still here, right? So this part is that, but this +1 is still here. I cannot forget that. So I've got the sum of j equals 1 to m omega j times 1 here, right? So that is still there, plus j equals 1 to m omega j. That is actually tan h aj. Good. So now I can just redefine the terms to get u's. So this becomes u0, and then there is actually a 2, right? So because tan h is 2 times sigma, so I should have put a 2 here. Nobody called me this time. You're usually much more careful. So I made, by the way, all corrections in the solutions. Thanks to all, to everyone who has kind of pointed out typos. Yes, there has to be a 2 here and divided by 2 here. So 2 sigma and then divided by 2. And then -1 + 1. That's also like this. Okay. No, there has to be the parenthesis. Yep. Yep. Okay, because of this 2 here and then that. So we have done the tangent, hyperbolic is there, and then u0 is there, omega j over 2, then this becomes then the uj. And I have the equation that I was looking for, which is this. So that is the, I converted one basis set to the other basis set. Yeah, but you see this is a linear, I also noticed that we have seen 2 different linear models, regression models. One is using the sigmoid functions as the basis functions, and the other one is the tangent hyperbolic as the basis functions, right? Equation 3, this equation 3101 and 3102. So these are 2 different models for doing linear regression, and they are of m degree. So that's a hyperparameter that needs to be dealt with. All right. So that's the story there for this question. Let me see. I think we ran out of time. So next week, Wednesday, I will continue. I have to continue. There is only limited time in the subject. So I will continue with this stuff on Wednesday. Then Thursday, we have the exam. Then the week after, we'll continue again. No workshops next week, right? Also, just to keep it in mind. And the reports are due Monday, as you know. And then you know where to upload them as well. Thank you, and see you next week.